Hey kids, Mr. Murray's Mathland here, and today we're talking about local linearization in calculus. So take a look at this problem here. For this function f of x equals sine of 2x plus 5, we're going to use linearization to estimate the value of f of 0.2. Obviously I say estimate because if you try to evaluate f of 0.2 without a calculator on your own, you'll get sine of 0.4 plus 5, and that's certainly not off the unit circle. And 1700 or so, when Isaac Newton and Leibniz were creating this stuff, they didn't have calculators. So we're gonna learn one way to estimate, and that's with linearization. And the key part of that is line. So we're going to write a tangent line at a point that's nearby, which is why it's sometimes referred to as local linearization. A point that's nearby that I do know. So for example, near 0.2, what's the nearest x value on the unit circle that I could plug in, I could evaluate? I would say that'd be 0. So we're going to write the tangent line at x equals 0. And a lot of times I'll tell you, or the problem will tell you what x value to use. You won't have to decide. But that's sort of the logic here. One that's close by the point you want. So at x equals 0. So if I want to write a tangent line at 0, that's pretty classic basic stuff, right? We need the point. So I'm going to plug in 0, and so I get sine of 2 times 0 is 0. Plus 5, sine of 0 is 0, and 0 plus 5 is 5. So, hey, my point of tangency is 0, 5. And then for my slope, of course, this was the point. For the slope, I need the derivative. So my derivative of f of x equals sine of 2x is f prime of x is, and that would be cosine of 2x, and so don't forget that chain rule there. We got to multiply by the derivative of the inner expression, so times 2. The constant of plus 5 just drops out, and so now that's the derivative, but I need the slope at x equals 0, so I plug 0 into that derivative. F prime of 0 is 2 times the cosine of 0. Cosine of 0 is 1, so 1 times that 2 gives me a nice slope value of 2. So my tangent line is y minus 5 equals the slope 2 times x minus 0. And since it's x minus 0, why don't I just, call that x, and so times 2. And why don't I move the 5 over while I'm at it? So why not? So it's y equals 2x plus 5. Now that's the tangent line. And then I'm going to use that to estimate the value of 0.2, so of f of 0.2. So here's the idea, right? F of 0.2, I'm going to plug 0.2 into this tangent line. And so basically you're getting the y value on the tangent line, and that should be pretty close to the y value on the curve. And if you can't visualize what I'm talking about, we'll check that out in a minute. So 2 times 0.2 is 0.4, and 0.4 plus 5 is 5.4. Sorry, that took me so long there. It's challenging stuff. Addition. So I have the f of 0.2 is probably in the ballpark of 5.4. Now the question also asks me to determine whether this estimate of 5.4 is more or less than the actual value of f of 0.2. But before I get to that, let's talk about why this is a decent estimate, and this will help us sort of judge whether it's more or less. So if you're sort of confused as to why we're even doing this, besides the fact that it said linearization, and so that meant write a tangent line and just plug stuff in, let's try to picture this curve here. F of x is a pretty basic sinusoid with 2x plus 5, so it's got a midline of 5, That b value on the inside is 2, so its period is going to be pi. And so that would be pi over 2, pi over 4. This is super rough sketch, but a good review of all that stuff you should know. And so the amplitude is 1 because of that coefficient in front of the sine. So the highest it's going to go is 6. The lowest it's going to go is 4. Certainly this is not drawn to scale. And sine would be right here, and the next value would be its maximum. Then on the midline, then back 1 unit below for that trough, and then completing the cycle at pi. So there's the sinusoid. And what I'm trying to do is I'm trying to estimate, well, what's the value of f of 0.2 on this? And so f of 0 I know is 5. Right? That's why we chose that point, because it was a nearby point. F of 0.2 would be right about there, and I don't know that y coordinate. That's what I'm trying to estimate here. But what I did just do is I just wrote the equation of this tangent line at 0, 5. So I wrote this tangent line, and it's certainly not a perfect drawing here, but okay, now if I were to zoom in there on that, I really want you to see that there, of course, the tangent line and the curve only intersect at that one point of tangency in that local neighborhood. And when I plug in 0.2 into that tangent line's equation, because this is what's y equals 2x plus 5, you can use a y-intercept of 5, a slope of 2. When I plug 0.2 into there, I'm getting the y-coordinate on the line. But you see how close that is to the curve, that's why it's probably a decent estimate. On the line, the x value is 0.2 and the y value is 5.4. So this value that I really care about is probably in the neighborhood of 5.4. And as far as whether it's more or less, hopefully you can visualize this based on my rough sketch. But maybe you can see that because they're together right here, but after that they diverge, the curve and the line, and they get further and further apart the further you go away from that point of tangency. But as soon as I'm sort of diverging, the line is above the curve. The line is always going to be above the curve in that neighborhood. So my estimate is going to be more than the actual value. So the true value of f of 0.2 is less than 5.4. Oh, sorry, I didn't always answer the question the way it's asked. That's an AP thing there. And they ordered it as, is my estimate more or less than the actual value? So my estimate of 5.4 is greater than or is more than the actual value of f of 0.2. Sorry about that. Always got to read your question carefully. Everybody does. And we can see now. Let's bring in a little technology here, and let's just see. So for sine of, let's see the actual value of f of 0.2. So when we plug 0.2 into this function, we get sine of 0.4 because it's 2 times that 0.2 plus 5. We should see that it's close to 5.4, but probably a little bit less. How far off? I don't know. This is just a decent estimate. But look, it's just by writing the equation of a line, I got a pretty decent value of 5.38, which rounds to 5.4. So not too bad here. And you could see if I were to plug in values that were further away from 0, like I was saying, if I were to plug in 0.4 into it, those y values on the line would start to be further away from the y values on the curve. So, for it to be a decent estimate, it's got to be in the neighborhood. That's why it's called local linearizations, in the local neighborhood of that point of tangency. Now in the future, when you're asked about these estimates, whether they're more or less, you won't always know what the graph looks like. This was just a nice example to build off something we know, a sinusoidal graph. But if you don't know what the graph looks like, there's one specific trait of the line that really tells you whether it's the tangent line is going to give you a greater or a smaller estimate value. So it has to do with what we call the concavity, and we haven't gotten into that too much at this point in the year. But on this part of the graph where it's concave down, you can visualize that anywhere I draw a tangent line on that, if I were to draw a tangent line over there, if I were to draw it, right here, there, anywhere you draw a tangent line on a part of a graph that's concave down, your tangent line is going to be above the curve, except for that point of tangency. If I were to draw it to this region of the graph, where it's concave up, you can visualize it. It doesn't matter where I draw it in here, anywhere I draw a tangent line, now the tangent line is going to be below the curve. So that's what it's really all about when we go further with this, is it's about the concavity of the graph. Will tell you if your tangent line approximation is more or less. So that gives you an idea of, we've got an estimate, but I know my true value is a little bit more or a little bit less, depending on the concavity. And the concavity, you may recall, we touched upon this, has to do with the second derivative. And, we'll be getting, more heavily into that this chapter. But, so maybe this is too much information right now. But hopefully give you a good idea of what we're all about here with linearization and why it could be useful and what you could do with it. So if you have any questions, as always, reach out and keep working hard, kids.